Good morning YouTube, and welcome to today's worked exam answer video. Following on from last week's Mastering the Gibbs Free Energy equation with Miss G video, I thought today it might be helpful to do a worked exam answer video to showcase how to implement the skills that I showcased in last week's video. So in this question, we are being asked to do two things. First of all, to calculate a value for the free energy change at a particular temperature using the value for the enthalpy change provided and using the entropy data that we've been given in that table. And then the second part of this question is calculating a value for the temperature when the reaction becomes feasible. So this is a pretty standard layout for a Gibbs Free Energy equation question. Let's dive in and give it a go. So, as lots of you will be used to by now, I started this question by picking up on a few key things. So, the units of entropy are in joules per Kelvin per mole. Now, there's two things that then pertains to. One is the fact that the units for delta H are in kilojoules per mole. So there's a mismatch in the units there. And the other being that the entropy is in per Kelvin per mole, and we have a temperature in degrees Celsius. So there's two unit conversions I needed to do there, and I converted my temperature from degrees to Kelvin straight away, and then when I calculate my value for delta S, I then immediately convert that into kilojoules per Kelvin per mole, and I'll come back to that in a second. The other thing that I picked up on was the presence of this balancing number in our equation, and the fact that the values provided for the entropy for these different substances again are in joules per Kelvin per mole. And I have 3 moles of H2 in my equation. So just to remind me and draw my attention to the fact that in my calculation I'm going to need to do something about that too. So the first thing I then did was I wrote out my delta G is delta H minus T delta S equation, and then I knew I already had a value for delta H, minus 49 kilojoules per mole. I already had my value for temperature, which I'd already converted into Kelvin, so that left me then needing to calculate a value for the entropy change. Now, to work out the entropy change of a reaction, we do the sum of the entropy values for the products minus the sum of the entropy values of the reactants, and that's why the balanced chemical equation is there. So methanol and water in the gas phase are our products, so I added those together, and then for my reactants we have CO2 and the 3 lots of H2. So anytime you have more than 1 mole of a substance in your equation, you are going to have to multiply the value you are provided with by that number of moles. And I worked out what that was, and that gave me a value for the entropy change of minus 180 joules per Kelvin per mole. Now, as I've already alluded to, the units for entropy and enthalpy are different, so I need to get them both into kilojoules per mole because the units for delta G are in kilojoules per mole. So I've then divided that value by 1,000 to get 0.18 kilojoules per Kelvin per mole. Now, I always think it's a good idea just to check that the value we get for the entropy change is what we would expect it to be. So entropy changes can be positive or negative, and that reflects whether there is an increase or a decrease in disorder as we progress through the reaction. So the fact that I got a negative value for delta S would suggest that there is a decrease in disorder that occurs as this reaction proceeds, which, if we have a look at the balanced chemical equation, is to be expected. We've got more moles of gas in the reactants and fewer moles of gas in the products. There is going to be more disorder initially because there are more moles of gas and less disorder at the end. So there is going to be a decrease in disorder of the system. So delta S should be negative, and it is. Just a nice little check that you can do. Then, because I've now got my value for delta S, I can put that into my equation. Now that is going to end up giving me a value for delta G that is positive because we have minus 49 minus 94.14. And when delta G is positive, the reaction is not feasible. Now, it hasn't asked me to comment on the feasibility of this reaction based on the value we calculated for delta G, but some questions will. So if it says comment on what this value for delta G tells us about the feasibility of a reaction, if delta G is positive, the reaction will not be feasible at whatever temperature you have used. So at 523 Kelvin, this reaction is not feasible. That's why the follow-on part of this question is asking us to calculate a value for the temperature when the reaction does become feasible. Now, again, if we just have a look at the equation, we can kind of see what temperature, again, we're expecting to get here for a reaction being feasible. So for delta G to be 0 or less than 0, we need the number that we calculate for T delta S to be smaller than the value for delta H, so that we are adding a smaller number than 49 so that we stay at 0 or stay underneath 0. So we're going to need a lower temperature than 523 Kelvin to achieve that. So let's see exactly what temperature we're going to need. So whenever it asks us to calculate a value for the temperature when the reaction becomes feasible, we set delta G to 0, because that is the first point at which the reaction becomes feasible, and then delta G will become negative. So I've rewritten out my Gibbs Free Energy equation, but I've got 0 equals delta H minus T delta S now, and then I just need to rearrange this to get temperature as the subject. So I take the negative T delta S over to the left hand side to get rid of the negative, and then I divide through by delta S to get T on its own. Using the same values for delta H and delta S from the question above, we can see that the temperature we would need for this reaction to be feasible is 272.2 Kelvin, which, as I predicted, is less than the 523 we had before. Hopefully that's been helpful. Any questions, as always, please hit me up in the comments or via social media, or drop me an email. The link to that will be in the video description. Wishing you all a really wonderful Tuesday. Thank you for watching.